We are now moving on to our next unit, and the focus of this unit is finding the vertex of a quadratic relation using two new methods. We will also look at the final form of a quadratic relation called vertex form. So today we're going to learn how to use symmetry, also known as partial factoring, to determine the vertex of a parabola. So let's go back and do a bit of review. How can you determine the coordinates of the vertex for a quadratic given in standard form? So recall in standard form, we have y equals a x squared plus bx plus c. And to get the coordinates of the vertex, we first need to convert this to factored form. So y equals a, x minus x1, x minus x2. And then once we have it in our factored form, we can find the zeros. We let y equal 0 and solve for each of the factors. Once we have the zeros, we can find the axis of symmetry. And we use our formula x equals x1 plus x2 divided by 2. And once we have the axis of symmetry, we can sub our x value into standard form or factored form to get the optimal value. And once we have the optimal value, we have our vertex. So recall our vertex is our axis of symmetry and our optimal value. So let's go through our first example here. Determine the coordinates of the vertex for each quadratic relation shown here. So step 1, we need to factor this expression. So let's start by common factoring, and the only common factor here is the negative. So we're left with 2x squared minus 12x plus 13. And to factor this expression, we need two numbers that multiply to a times c. There's our a, there's our c, which gives us 26, and add up to b. And our b is our middle term there, and that is negative 12. So let's look at factors of 26. So we have 26 and 1. Those do not add up or subtract to give you negative 12. We have 13 and 2. Adding those do not give you negative 12, nor does subtracting. So this is where we get to a case where we cannot factor this expression. So we need to find another method to find the vertex, if one exists. Let's try the second one. The second one we don't need to factor. But again, we need two numbers that multiply to 7. So a times c is 7. And which add up to our b value. And our b value here is 4. And the only factors that you have for 7 are 7 and 1. And 7 plus 1 does not give you 4, nor does 7 minus 1. So again, we have another example which you cannot factor. So we need a method to determine the vertex. So let's take a look at these two equations more closely. So in example 2, I want you to determine the vertex for each quadratic by graphing each of the following quadratics using the table of values given here. So take a moment now, pause the video, and see if you can find the y values for the given x values. So hopefully you've tried that out. Here are the y values: negative 3, 3, 5, 3, and negative 3. So let's graph that. So at 1, we're at negative 3. 2, we're at 3. Then we get up to 5 for the next value of 3. Then back down to 3. And all the way back down to negative 3. So notice this is a parabola. It has a maximum value. And it clearly has a vertex. So we see our vertex right here, and we note from the table of values or from the graph that the vertex is 3, 5. So why is this not factorable? Well, if you look at the graph, it does cross the x-axis, so it does have two zeros, but these zeros are what we call irrational roots. They are zeros that cannot be expressed as a fraction. So this one has two zeros. However, the zeros are irrational numbers. And again, that means they cannot be expressed as a fraction or an integer value. So this is why it's not factorable. If you tried the second one, our numbers are 7, 4, 3, 4, and 7. And if we graph this, we notice that again, this is a parabola. In this case, it opens up, and this time we have a minimum point, and our vertex is here, and we can get that from the table, or we can see it from the graph, that we have a vertex of -2 and 3. And this one, we note, has no zeros. So this one cannot be factored. So in the first example I gave you, it does have two zeros, but they are irrational numbers, so with our grade 10 methods, we cannot factor this. And for B, the parabola has no zeros, it does not cross the x-axis, so therefore this one does not have a factored form. So now we're going to look at a method that can find the vertex of a quadratic, whether or not it's factorable, and whether or not it has zeros. So this method is called partial factoring, or I like to call it symmetry. The key step is looking at that C value, -13. If we go back up to the graphs, if we look at the C value for this one, which is 7, we notice that the 7 is where it crosses the y-axis. And in the symmetry method, we're going to use that 7, and then we're going to also find its corresponding point here. So what is that point? And once we have those 2 points, if we take the average of those 2 points, since they're equal distance from the axis of symmetry, we can now find the axis of symmetry. We can then get our optimal value. So let's go through our symmetry method. So step 1, from the C value, we see the y-intercept for this relation is 0 and -13. So we're going to let y equal -13. That is our first step. And if we sub that in, we get -13 equals -2x squared plus 12x minus 13. That is always going to be our first step for symmetry. The second step is using this equation, we're going to solve for the roots. And this is a similar thing as solving for the zeros. So to do this, we are going to get rid of the -13 from the one side. So to do that, we're going to add 13 to both sides. And then what we're left with is 0 equals -2x squared plus 12x. So now this is what we call an equivalent expression. And this equivalent expression, we're going to use the same methods we used last unit and solve for the zeros of this expression. So to do that is to first factor. So we can see with these two terms, it's just a common factor of -2x. And we're left with x minus 6. So the next step now is to solve for each of those factors. So we get -2x equals 0 and x minus 6 equals 0, which tells us that our first 0 is 0 and our second 0 is 6. But again, these are called roots. They're the zeros for this equation, but they're the roots for the equation we started with. So these 2 points that we see here, where x equals 0, notice we subbed in y equals -13, so that is going to be that point there. That is our y-intercept. Then where our x2 is 6, that's another point with the same height at -13, or the same y value. Now that we have these 2 points that have the same y value, we can find the axis of symmetry. So step 3 is determine the equation of the axis of symmetry using the roots. So x equals x1 plus x2 divided by 2. We get 0 plus 6 divided by 2, and we get that x equals 3. That is our axis of symmetry. Now that we have the axis of symmetry, we can determine the optimal value using the equation from above. So we're going to sub x equals 3 into our equation y equals negative 2x squared plus 12x minus 13. And what we get is y equals negative 2, 3 squared, plus 12 times 3 minus 13. And using order of operations, we get negative 18 plus 36 minus 13. And if we simplify that, we get 5 for our optimal value. And the last step, state the coordinates of the vertex. So using the axis of symmetry and optimal value, we now know that we have a vertex xy, which equals 3, the axis of symmetry, and 5, the optimal value. So there is our vertex. The nice part about this is we now have 3 points for the graph. We have the points 0, negative 13, 6, negative 13, and we have the vertex 3, 5. So now we can sketch this graph. So if we take our axes here, we use our points. So we had 0 and negative 13. That was our first point. Remember, that is our y-intercept, which is the c value of the quadratic equation. And then over here we have 6 and negative 13. And we know our vertex, which is in the middle of these 2 points, is at 3 and 5. Notice the parabola opens down, which is good because if we looked at our original equation, we had a negative a value, which should give us a downward opening parabola. So that is our symmetry method, or partial factoring. So we're going to do 2 more examples using this method to help us find a vertex of a quadratic, whether or not it's factorable, and whether or not it has zeros. In this one, you see there are 2 zeros. Is this factorable? It could be, but this method is much quicker than the factoring method and guarantees you're going to find a vertex. So let's go through the symmetry method once again. So first step is to let y equal the c value, which is the y-intercept. So that is 7. So we have 7 equals x squared plus 4x plus 7. We're going to minus 7 from both sides because we want to get an equivalent expression in terms of 0 because we know how to solve for zeros. Next step is to factor, and it's always going to be a common factor if you use the symmetry method. Find your roots. So this would be x equals 0. This would be x plus 4 equals 0, which means that x2 equals negative 4. Once I have my zeros, I can now get my axis of symmetry, which remember is x equals x1 plus x2 divided by 2, which is 0 plus negative 4 over 2, which equals negative 2. And then last step is to get my optimal value. So I'm going to have y equals, and I'm going to sub negative 2 into my original equation, and then solve for y. And if I do that, I get y equals 3. So therefore, my vertex is, using the axis of symmetry and the optimal value, negative 2 and 3. All right, let's try the last one. So again, let's start, what is the c value? And remember, the c value is the y-intercept. So our c value here is negative 1. So we're going to let y equal negative 1. So we get negative 1 equals 7x squared plus 21x minus 1. We're going to add 1 to both sides to get rid of that negative 1. We get our equivalent equation. which helps us solve for the roots. We common factor, and the common factor here is 7x. We solve for each of the factors, so we get x1 equals 0, and notice our x1 is always going to be a 0, and our second 0 will be the corresponding point with the same y value. Next we need the axis of symmetry, which is x equals the first 0, or root, plus the second root, divided by 2, which in this case gives us negative 3 over 2. The next part is to get our optimal value, which is y equals 7, and we sub in our axis of symmetry, and we solve for the optimal value. So that's going to be 7 times, remember that's 7 over 1. If we square that, that's 9 over 4. 21 over 1 times negative 3 over 2 minus 1. So if we solve that, we get 63 over 4 minus 63 over 2 minus 1. So the next part is we need a common denominator. So that's 63 over 4 minus 126 over 4 minus 4 over 4. And now we get to solve for our vertex. And this gives us negative 67 over 4. This tells us that our vertex this time is negative 3 over 2 and negative 67 over 4. Before we finish, let's take a look at what these parabolas would look like. So let's go back to our first one here. So first point we have is our 0 and 7, so that would be here. The second point we have is negative 4 and 7. That would be this point here. And then we have our vertex, negative 2 and 3. And notice, when we sketch this parabola, we have a parabola that opens up, which relates to our a value, which is positive. The 3 points we have this time, so starting with the 0, remember we let y equal negative 1, so that's 0 and negative 1. We also found the second corresponding point as negative 3 and negative 1. And we now know the vertex is in between these two, and it goes down to negative 67 over 4. Is approximately negative 16.75, or is exactly negative 16.75. So if you want, we can say this is negative 1.5 and minus 16.75. And there is our sketch. Again, the parabola opens up as it should because we have a positive a value. So again, the symmetry method is a much better way to find the vertex of a quadratic because you don't need to worry about whether or not it's factorable and whether or not it has zeros.